Imagine waking up in the morning and seeing an ordinary landscape outside the window, a branch, a bird, a cloud, a thin blue strip of air above the rooftops. Nothing reminds you that this picture has already vanished entirely several times. Not individual species, not a single continent, not yet another capital city, but a combination of sky, ocean, and living beings which never returned again. The Earth has kept the same address, but several times it has changed its contents. The Moon appeared after an impact that turned the surface of a young planet into an ocean of magma. Oxygen, without which we would last only minutes, was once waste produced by bacteria and poison for most of the inhabitants of that time. There were epochs when ice reached almost to the equator, and then the world suddenly filled with bodies, with eyes, and with predators. And 66 million years ago, one stone cleared the way for mammals, even though the impact itself lasted less than a human lifetime. In this episode, we will assemble not a museum of 5 ends of the world, but a map of causes. What exactly turns a catastrophe into a shift of worlds? Why does a planet sometimes return to its previous state after an impact and sometimes assemble into a different one? And what matters most, how do you tell an ancient fracture from a beautiful but overly confident legend? We will go from the Moon to oxygen, from global ice to the first complex ecosystems, and then to the crater, which today is hidden under water and sediment. In the end, we will return to the air above our heads and ask whether we are now living inside another reassembly. The first important thought is simple: the Earth is not the same as the world. The planet is about 4.5 billion years old, but the world can be called a specific combination of the atmosphere, the surface, the ocean, and the main forms of life. The planet survives an eruption or a meteorite fall. The world after that may not survive itself. If similar conditions return after millions of years, and the same large groups of organisms come back, that is a severe crisis, but not necessarily a new world. But if the chemistry of the air changes, the color of the sky, the shoreline, and the set of species which determine the food chains, a different countdown begins. That is why the number 5 is not a school list of mass extinctions. It is a working ruler for our story. 5 breaks, after which the previous combination never came together again. Such a boundary almost never has a round date. Geologists see it as a layer, a change in isotopes, the disappearance of a mineral, or a new set of fossils. There is no tablet with the inscription, "The world ended here." There are many independent traces that converge at one point. Let us begin with the most literal reassembly. Before the Moon, there was no familiar disk above the young Earth. The surface was cooling after the birth of the planet. Water had not yet formed a stable ocean, and the day was much shorter than it is now. Next to the Earth moved another body, roughly the size of Mars. We call it Theia, but this is not a name from an ancient document. It is a convenient label for a model. About 4.5 billion years ago, the orbits of the two bodies crossed. The impact most likely was not a direct head-on collision. According to the modern NASA model, material from both planets was thrown into orbit, and then the Moon assembled from it. The word model matters. There are no direct witnesses to the event, and the details of the impact angle are still being refined. But the lunar samples show a close kinship between the Earth and the Moon material, and the Earth-Moon system carries too much rotational energy to be explained by a simple, accidental encounter. The collision can be examined in seconds as an experiment without a camera. Kinetic energy does not disappear. It turns into heat, melts rock, and ejects part of the mantle into space. On the surface of the young Earth, no neat bowl remains because liquid rock does not preserve the shape of a crater the way solid rock does. The place of the impact ceases to be a separate place. The entire upper shell of the planet becomes part of one hot system. After cooling, the Earth acquired the Moon, the tides, and a new rhythm of rotation. The Moon is not a decorative lantern in the night sky. Its gravity breaks the Earth's rotation and stirs the coastal waters. Direct records of the earliest epochs have not survived, so estimates of the length of the ancient day are derived from models and geological markers. This is a useful limitation. Even the most striking number in the planet's history must carry the label estimate if it cannot be measured directly. But to call this impact an ordinary extinction event would be wrong. Before it, there was no familiar biosphere that could simply be lost. The first version of the surface ended, and with it, the previous sky disappeared. This was a catastrophe not because some known animal died, but because the very scene for future life was melted and assembled anew. The next break happened without an asteroid. It began with creatures that cannot be seen with the naked eye. On the early Earth, oxygen was not a gift to the atmosphere. Cyanobacteria produced it through photosynthesis. But at first the gas was bound by iron and other minerals in the ocean. In the rock, this left red bands and layers of iron formations. When the chemical traps began to fill, oxygen started to accumulate in the air. NASA Earth Observatory, describing the Great Oxidation Event, points to an interval around 2.4 billion years ago. This was not a single overnight shift in atmospheric composition. Oxygen concentrations rose in steps with setbacks and regional differences. For organisms accustomed to an oxygen-free environment, the new gas proved to be a reactive poison. Some lineages disappeared, some hid in silt and hot springs, and a few learned to use oxygen as a powerful source of energy. There is a paradox here worth remembering. The most destructive chemical revolution in life's history was launched not by a predator and not by a volcano, but by the metabolism of microscopic cells. Their waste turned the oceans into an archive of rust, altered minerals on land, and prepared the engine for future large organisms. On a human scale, waste is what needs to be carried out of a room. On a planetary scale, waste sometimes becomes a new atmosphere. We often tell the story of evolution as a ladder, where increasingly complex life gradually climbs upward. The Great Oxidation Event is more like a change of rules. Oxygen allows more energy to be extracted from a single portion of food, but it requires defense against oxidative damage. New enzymes, membranes, and modes of cellular repair emerge. The following billions of years were not a direct result of a single gas, yet without this gas, many large bodies, including ours, would not have received the energy budget. A trace does not necessarily look like a skeleton. Geologists look for the disappearance of minerals, the shift of sulfur isotopes, the appearance of red continental rocks, and changes in the composition of marine sediments. Quick referral also helps. NOAA, National Centers for Environmental Information. Its paleoclimate collections combine data on ancient temperatures, ocean chemistry, and atmospheric composition. Such an archive does not tell the story in ready-made paragraphs. It allows one to check where a beautiful reconstruction ends and a measurable signal begins. Oxygen did not create a calm world. It made it more energetic and more dangerous. The air became breathable for future complex life, but a great many previous niches vanished. The second Earth ended not with a wall of flame, but with slow poisoning for some, and the ability to breathe for others. Then the planet chose the opposite. Several times in the Neoproterozoic, an ice sheet spread so far that Earth is called a snowball. The name sounds definitive, but the data leave room for debate. Could open water have persisted in equatorial regions? Was the surface entirely frozen over, or was there instead a slush ball, a wetter, more heterogeneous version of freezing? NASA Goddard Institute for Space Studies, in its article, Snowball Earth Might Have Been Slushy, highlights two major episodes roughly 640 and 710 million years ago, and emphasizes that their chosen places and degrees of coverage remain serving of modeling. This is a good example of scientific honesty. The name of a hypothesis is remembered more easily than the range of uncertainty, but it is precisely the range that makes the conclusion more fallible. Ice intensifies cold not because it is magical in itself, but because it reflects the sunlight. The more white surface there is, the less energy the planet absorbs. Feedback loop. Freezing accelerates further freezing. Volcanic sources, meanwhile, maintain their release of carbon dioxide. If the ice cap almost does not participate in the minimum and does not absorb carbon, the gas accumulates in the atmosphere. After a very long time, the greenhouse effect becomes strong enough land to begin retreating. Imagine this not as a button to start spring, but as slow pressure against a closed door. Volcanoes add gas, but the ocean under the ice nearly does not exchange with the air. When the melting threshold is finally crossed, the surface changes rapidly by geological measures. Dark water absorbs more light, melting accelerates, and ocean chemistry restructures itself. It is not a single snowflake that saves the planet, but a chain of feedback loops that first drills the climate into a trap and then extracts it. The ice ages left behind unusual rocks, cap carbonates which lie on top of glacial deposits, as well as traces of glaciation on ancient continents that were once located near the equator. NOAA and other paleoclimate archives cross-reference these traces with magnetic data and the composition of minerals. These events are free from different source material. We see not a film, but a handful of confirmed data from that area of scientific modeling. From them, one can reconstruct the direction of movement, but one cannot honestly draw in every minute of a single line. Why did this catastrophe become a changing of the world? Because the ice covered the familiar ecological ties and reshadows the chemistry of the seas. Surviving organisms found themselves in narrow refuges, and after the retreat of the ice, they received a planet with a different amount of oxygen, different shorelines, and a different set of nutrients. The third Earth was not doomed by a single blow. It was compressed, withstood the pressure, and emerged from it no longer what it had been. Hundreds of millions of years later, a strange change of scale appears in the record. In Cambrian rocks, bodies become more diverse. Some acquire hard coverings, complex eyes, limbs, and traces of burrowing. This is sometimes called an explosion, as if life had suddenly been granted permission to experiment. But the explosion lasts millions of years, not seconds, and its causes cannot be reduced to a single convenient explanation. Smithsonian Ocean, in materials on the Cambrian explosion, shows how several factors coincided: the rise of oxygen, the development of predation, the emergence of new modes of locomotion, and the mineralization of bodies. When an animal can see and move quickly, others must defend themselves, hide, or become faster. Evolution turns into a race in which one species' innovation changes the conditions for all its neighbors. What matters is not only a new body form, but also a new geography of traces. Earlier, soft-bodied organisms left little information in rock. Shells and skeletons are preserved better, so part of the explosion is related to life having become more visible to a future geologist. This does not cancel biological acceleration. It adds an observer effect to it. The world may have changed, and at the same time, learned to leave a more detailed record. The Cambrian ecosystem was not a comfortable dawn, but a dangerous place. The appearance of eyes turns the landscape into a hunting tool. Burrows change the chemical exchange between water and sediment. Hard coverings allow one to survive an attack, but they require energy and minerals. Every new capability creates a new debt. Thus, complexity does not appear on its own. It is paid for with oxygen, food, and risk. This turning point shows why a change of worlds does not always look like extinction. Sometimes the main signal is the emergence of a new tempo of interactions. Water, the seafloor, light, and the body begin to work in a different configuration. The fourth Earth became a place where animals did not simply live side by side, but actively changed the living conditions of one another. Then the planet repeatedly changed the arrangement of continents. Continents merged into supercontinents and split apart. Ocean straits opened and closed, and with them, currents and heat transport were restructured. This is not one of the 5 instantaneous catastrophes, but a slow mechanism that makes each subsequent world possible. The position of land determines where clouds go, where glaciers form, and which seas remain shallow. NOAA paleoclimate data show how scientists use oxygen isotopes, fossil pollen, marine microfossils, and ancient soils to reconstruct such reorganizations. One proxy is rarely sufficient. An isotope may reflect temperature, but it can also depend on water composition. Pollen tells about vegetation, but only where it has been preserved. A reliable reconstruction emerges when different archives support one another. This is an important lesson for the modern planet. We look at a map of continents as a backdrop, although the map itself is a climatic instrument. A narrow strait can intensify a current. A high plateau changes seasonal precipitation. A forest that grows on a new shore begins to pump water into the atmosphere. The Earth does not simply react to life. Life gradually becomes part of the geological system. The most famous boundary occurred much later, about 66 million years ago. In the area of present-day Yucatan, a body struck, leaving the Chicxulub crater, most of which is hidden beneath sediments and shallow water. In the first minutes, the problem was not only the crater itself. Dust, soot, and vaporized rock rose into the air. Sunlight dimmed, vegetation lost energy, and food chains began to break from the bottom up. NASA Science, in the article Deep Impact and the Mass Extinction of Species 65 Million Years Ago, links the impact to a geological boundary and the mass disappearance of species. In the scientific text, the date is rounded because different methods yield small discrepancies. Today, one usually speaks of 66 million years. The estimate of the share of species that disappeared also depends on which groups are counted and where the sample is taken. So the number around 3/4 is the result of many studies, not the reading of a single counter. Here it is especially easy to get the image wrong. A shot of a fireball is impressive, but the main killer worked longer. Cold, darkness, hunger, acidity of precipitation, and the destruction of forests. Small animals and species capable of feeding on remains gained an advantage. Some birds survived the boundary, but this does not mean that the forest ecosystem continued unchanged. A branch survived, not the former world. Paleontologists find a thin layer of iridium, impact minerals, and deformed quartz. Taken together, these markers link a distant extinction to a specific cosmic event. NASA does not claim that the entire history of life is determined by asteroids. Deccan Traps volcanism and long-term climatic changes also affected the biosphere. But the coincidence of the impact layer, the timing of the extinction, and the global signal makes Chicxulub the strongest candidate for the main trigger. The user is asking me to translate a Russian text into English. They've provided clear instructions. Preserve every fact, name, number, example, qualification, tone, and sequence. Don't summarize or omit anything. Preserve paragraph order and blank line separators. Keep the narration length suitable for video scene timing. Return only the translated text block without any formatting. The source text is a continuation of what appears to be a documentary script or educational narration about Earth's history, mass extinctions, and the geological evolution of the planet. It discusses the 5 major transitions in Earth's history, scientific methods for studying them, and the current 6th transition that humanity is witnessing. Key considerations for the translation. 1. The text has a contemplative, explanatory tone. This should come through in English too. Technical terms need accurate translation. Spuskovoi krючок as trigger, paleoclimate terminology, earth science concepts 3, proper names and entities, NOAA, ANCEI, NASA Earth indicators, Chicxulub, Chicxulub 4. The text discusses geological timescales, extinction events like the oxygen crisis, Snowball Earth, the Chicxulub impact 5. Paragraph structure must remain intact with blank lines between paragraphs. The text contains well-reasoned scientific discussions about how the current change is being measured, how planetary stability operates on different timescales, and the distinction between extinction of species versus loss of ecological function. These nuances need to be preserved carefully in English. I'll translate this carefully, maintaining the logical flow, the formal but accessible tone, and all the scientific details without fluff or omissions. Let me work through the translation to ensure all facts are preserved and reproduced. The trigger. After the strike, large terrestrial animals disappeared, and the space that was freed did not remain empty. Mammals that had long lived in the shadow of larger forms received new roles. There is no moral tale of winners and losers here. The previous set of competitors simply no longer occupied every niche. The sixth Earth began with voids, not with a ready-made plan for human beings. Now let us try to view the 5 breakpoints as a single scheme. The first altered rotation and the satellite system. The second changed the chemistry of the atmosphere. The third closed and then reopened the climate machine. The fourth accelerated interactions among animals. The fifth collapsed terrestrial food webs. The triggers differ, but the outcome is similar. Not one parameter changes, but the coupling between several planetary spheres. Science assembles such coupling from traces of different scales. Isotopes speak of temperature and chemistry. Minerals show what happened in the water. Pollen and shells reconstruct ecosystems. Craters in the geological rocks are linked to impact events. Satellite observations add a modern frame, but they do not replace ancient archives. NOAA warns plainly, paleoclimatic records are heterogeneous, and reconstructions have ranges of uncertainty. This is not a weakness of the method, but its honest form. For that reason, we should not ask, what single cause eliminated the world? More accurate is to ask, what cause pushed the system across a threshold after which feedback did the rest? An impact can trigger a dark winter, but extinction is amplified by hunger and the destruction of habitats. A volcano may add gas, but the response is regulated by the ocean, the ice, and the continents. Bacteria release oxygen, but the outcome is determined by how much iron can bind it. There is yet another scale. The planet need not be stable to remain habitable. The sort of stability on a human timescale, even the regression we see in an intra-human timeframe, is a man-made pause before larger rearrangements resume. Over millions of years, the ocean rises and falls. Mountains are affected. They lengthen and erode. The composition of the atmosphere varies, and life turns those changes into new conditions. Our sense of permanence is explained not by the fact that the Earth is already flat at this point of calm, but by the fact that human life is too short, and an eye that is 2 billion years old is a narrow data center whose sensation is called watchfulness in a poetic sense. So what is happening now? NASA Earth indicators shows that the concentration of carbon dioxide in the atmosphere is at a level that has not been seen in many hundreds of thousands of years of observed climate history. And satellite and surface measurements allow us to track the change almost in real time. The exact maximum number updates over time, so we will not turn today's reading into an eternal slogan. What matters is different news. The source of the change is known, the rate is recorded by instruments, and the physical mechanism is tested with visible, conflict-checked rubric. Modern warming is not equal to an aftermath of an overnight catastrophe. There is no asteroid that would in seconds turn the surface into steam. There is also no proof that humanity has already reached the scale of ancient mass extinctions in terms of the number of species lost. But this is the first restructuring inside which there exists an observer capable of measuring the composition of the air, the temperature of the ocean, the melting of ice, and the disappearance of species within a single lifetime. An understanding of the sixth Earth lies in this difficult share. Ancient organisms could not look at a graph of oxygen content and compare it with last year. But we can. That means we have the opportunity to notice that no previous organism with ozone on a shorter mission could notice the entire turnover of carbon-calcium. Opportunity does not guarantee we will pick it at once, but it changes the status of a human being. We are no longer just tenants of the system, but one of its measuring instruments and at the same time, one of the factors of change. There is another reason not to turn this story into a catalog of terrible dates. After each restructuring, islands of continuity remained. The moon's transform did not create the planet from emptiness. It changed its rotation, the transitions, and the scale of the tilt of its orbit in a matter of a period, and the further old intricacies have then grown. The half-carat-old underscore code of blinks smaller, like 1 equals the moon 0. Every Thursday, useless jewel. And after the oxygen of the fixation crisis, not all of life disappeared. Oxygen-free communities were preserved in sediments and deep waters. Even after global glaciation, the ocean did not become a sterile, empty triangle. A temporary closure destroys connections, but not all organisms. Membranes perceive the shift through words such as survive and happen changed. A small colony of bacteria can outlast a global catastrophe for days with nothing to say about the medical fire risk next door, but the same biosphere would do if its main exchanges/metabolism were entirely silenced. So annoying. Description: to survive, or to persist. Explanation of difference via achievements source creates another lollipop list, chromosome attached to each schedule. His slideshow to write examples stand for the duality of danger tolerance, which by survival_list_item is untouched, derived in his capital asterisk list that makes a newbie sphere with objects //. And when many wares form diagonal, a shift has an already switches curvature change character. The audio track, end on, let's of the plan vision shift, do type start, most people with memoir appear, reads, someone on false fate, abrupt cut, al-muster, talking head from 1970s screen, Washington clear, source, by https://Halays, answers a modern street campet _unique letter /Lance, what shift echo, write a reading, a supplement. And they, correct, ESS straight to his threshold. Empirical airman, a word story. The user has provided a source text block in Russian and requested a professional translation into English. The instructions are clear. Preserve all facts, maintain paragraph structure, keep the same tone and sequence, and return only the translated text without any formatting. The source text discusses scientific topics including geological timescales, the moon's formation, the Great Oxidation Event, Snowball Earth, the Cambrian explosion, and the Chicxulub impact. It's written in an academic, explanatory style, weaving together different scientific narratives about planetary evolution and extinction events. The target language is English. The register is formal and informative, aimed at an educational or general science audience. Key considerations include maintaining scientific accuracy with terms like impact event, geological timescales, and relations of cause and effect. The text maintains a measured, exploratory tone about scientific uncertainty, using phrases like reconstruction should not promise precise assembly and how to describe feedback mechanisms confidently. I need to preserve the paragraph structure exactly as given, keeping the blank there and the narrative connections. Specific terms like NASA Science and NASA GISS should remain in English as they are already in this form. The translation should sound like natural English science writing while maintaining all the original comparisons and qualifications present in the Russian text of years and decades. Dust settled, but forests did not grow back the next day. Recovery of food webs lasted far longer than human history. Therefore, reconstruction should not promise precise reassembly. Scientists see a layer before the event, a layer of transition, and a layer after it. Between them, there may be a gap. Erosion washed away sediment, the ocean dissolved minerals, a continent rose and ended up above sea level. A mosaic is assembled from several locations. When two continents show the same signal, confidence grows. When the data contradict each other, it provides not a reason to pick the convenient option, but a new scientific challenge. So it happened with the history of the moon as well. Early versions of the giant impact assumed that the satellite consists almost entirely of ejected material from Earth. Lunar samples showed chemical similarity, but at the same time raised the question of how materials were mixed. More modern models allow that after the impact, KIP material from Earth and Theia could quickly exchange components. NASA science therefore describes the moon exploration as an ongoing investigation, not as a closed protocol. The moon also has an obscure climatic role. Tidal friction gradually pushes it away from Earth and slows the planet's rotation. It is not a climate switch, but an additional rhythm for oceans and shores. The longer does not the day, the solar heat is distributed differently between the day and night sides. We cannot honestly say that the moon alone created the conditions for life. More precisely, after its appearance, the planet acquired a new system of tides and rotation, into which the ocean and atmosphere later became integrated. The oxygen transition was also not a direct path to modern air. In the ocean, there were zones where oxygen appeared at the surface and disappeared in deeper waters. Sulfates, iron, and organic carbon bound part of the gas. Individual episodes of accumulation could be followed by collapses. The NASA Earth Observatory highlights precisely the gradualness of the Great Oxidation Event. We can describe the feedback mechanism with confidence, but the duration and extent of coverage should be treated as reconstruction. After the Great Oxidation Event, in rocks leave traces of unusually rapid chemical exchange, specifically warm water erases fresh rock. The ocean receives new elements, and shallow our shelf become laboratories for microbes and early multicellular organisms. Perhaps not the only explanation for this widespread explosion, but there are no clear solutions. It connects climatic and evolutionary histories without preserving cold Earth. There is no cold planet's own observer trap. When ice is abundant, rock outcrops are more visible, and rare marine concentrates, and a single lake can sample a climate preserving some simple housing. This is why significant damages are slow decay. The past few years has developed a significant emotional, but the duration and extent of coverage should be left as reconstruction. After the warm Earth, traces of fast melting and warm processes. The warm waters warm the atmosphere, the ocean receives new factors, across shallow waters becomes a bee-house for microbes and single-celled life. We need to recognize in the chapter on the surviving events. This last text continues, dark clouds are now one of the covers of future life. After the melting of the coldest glacier, organisms emerge from the platform. The first tropical zones cover the equator, their lasting partiality in the equatorial circulation, around dawn. But the environment is not a rotating tank. How long the sparse foods are reconstrained fractions of necessary chemical entropy. New deals could occur, heat from volcanions and mountain safety, each by each vault's cross, currently subordinate to one report, rise. So paragraph from original focus. The same bulk of data storage shows on Chicxulub of Snowball Earth. If there is much children, open access to old technology, exposed blocks, thereby foreign, snail prevails equals and they imply boiling loop. We need to write 500 millions year with careful gradient. If there is much ado, ancient exposed land is rare, and marine sediment can be mixed when a father type during theoretical science multiple times. The same stone can circulose ranges in a report. The depth of such writing is open today. Multiple stones can be greater than CNG, i.e. duration of the flood Dumiat, and long is evolving. Su, 2017, already. Ranging descriptions not equal to 1. Only physical background I could report confidence. The freezing of oxygen, not a permanent cycle. More recent models insist equally CO2 rise, and changes in equals host no different result. Then absolute that is odd reference to melting. We consider unknown alive mini equals, but the shape is uncertain, not must have data and course, I should pad. Continuation, but extremely high temperatures, here, mid-suspiciously, prefer cold exactly. Devonian, the fixed in hot and old, actually each limit with until camel. Potential, final transition. Snowball, material out after icehouse state, anomalously rapid com. Actually, the intermediate text runs. Кембрийские хищники заставляют иначе посмотреть на слово «прогресс». Животное становится геологическим агентом задолго до появления человеческих городов. Chicxulub показывает обратную сторону усложнения. No, logical. Potential. Chapter. Chicxulub equals accepted. Translate without these, turn back. Now final. Start with let and decade, but acceptable translation. Years and decades. Integral. Begin. Years and decades. Dust settled, but forests did not regrow the next day. Recovery of food webs took far longer than human history. Therefore, reconstruction must not promise an exact restoration. Scientists see a layer before the event, a layer of transition, and a layer after it. Between them there may be a gap, erosion washed away sediment, the ocean dissolved minerals, a continent rose and ended up on land. A mosaic is assembled from several locations. If two continents show the same signal, confidence increases. If data contradict each other, that is not a reason to choose the convenient option, but a new scientific task. This also happened with the history of the Moon. Early versions of the giant impact assumed that the satellite consists almost entirely of material ejected from Earth. Lunar samples showed chemical similarity but simultaneously raised the question of mixing of substance. More recent models allow that after the impact, to the U-Earth and Theia material could mix both ways. Thus, NASA science tells the story of the Moon's formation as an ongoing research topic, not as a closed protocol. The Moon also has a hidden climatic role. Tidal friction gradually pushes the Moon away from Earth and slows the planet's rotation. This is not a climate switch, but an extra rhythm for oceans and shores. The longer the day, the differently it is the day, but distribution of solar heat between the day and night side. We cannot honestly say that the Moon alone created the conditions for life. More precisely, after its emergence, the planet had a new system of tides and rotation, into which ocean and atmosphere later incorporated. The oxygen world was not a direct road to present-day air. In the ocean, there were zones where oxygen appeared near the surface and disappeared at the surface. Sulfates, iron, and organic carbon bonded part of the gas. Individual episodes of oxygen accumulation could be followed by collapses of those episodes. NASA Earth Observatory emphasizes precisely the gradualness of the Great Oxidation Event. First, the geological traps stopped keeping up with oxygen production, and only then did the atmosphere cross the threshold that changed planetary chemistry. An unexpected conclusion about the causes of extinction follows from all that. An organism can produce a resource that makes its neighbor stronger, and then find itself in an environment where its old way of respiration no longer works. Evolution Petroleum does not plan a result billions of years ahead. Bacteria have want to create an obsession with oxygen atmosphere. They shaped their local environment, and geologic time turned a local process into a global one. Snowball Earth has its own observer trap in itself. If there is much ice, ancient terrain outcrops are rare, while marine sediments can be mixed during melting. One and the same rock can weather within several climate states. That is why estimates of the glacial duration differ. NASA GISS speaks in ranges, not a single number. The same feedback mechanism can be described with confidence, but the duration and extent of ice cover should remain a reconstruction. After exiting the glacial state, rocks show traces of unusually rapid chemical features. Warm water erodes ice sheets, ocean gets new elements, and shallow shelves become laboratories for microbes and early complex organisms. Likely, it is the contrast between long isolation and abrupt opening of new resources that helped prepare the subsequent biological experiments. This is not the only explanation of the Cambrian explosion, but it links climate and evolutionary history without introducing a sudden miracle. Cambrian predators force us to look differently at the word progress. The eye is not simply adding a picture. It changes the distance at which ephemeral. The shell is not just protection. It requires minerals, increases animals' weight, and thus the means of movement changes. A burrow is not only hidden, it mixes the bottom sediment and changes oxygen supply. The animal becomes a geological agent long before the appearance of human cities. Chicxulub shows the other side of that trend. The longer the food chain, the more ways it can break. A plant does not get light. Herbivore loses food. Predator loses prey. In the ocean, the same chain runs through plankton. At the same time, freshwater systems sometimes withstand the impact better because they are usually eat detritus and receive nutrients from land. That is not a universal law, but a good example. Why the same disaster produces different results in different environments. Recovery after a meteor impact does not also return the old version. An empty trophy is not a ready-made apartment, but a place with changed conditions. A new inhabitant occupies it in a different way, and after a few million years, The ecosystem looks natural, although its composition has been shaped by a random sequence of survivors. What looks like a permanent order may be only a historical pause between two other cataclysms demonstrates. Modern measurements add another layer to this ancient story. NASA Earth Indicators updates the carbon dioxide series based on atmospheric observations and shows not only the number but also the direction of change. In parallel, NOAA collects oceanic and climate data that allow us to see how heat is distributed between air, water, and ice. We get something that organisms of the past never had, almost instantaneous feedback between cause and effect. But measurement does not make the system safe automatically. A graph can warn of a trend, but it cannot cancel the inertia of the ocean, the delayed response of ice sheets, or the long residence time of some CO2 in the atmosphere. Even if the source of emissions changes today, the planet continues to respond to accumulated forcing. This is not an argument for panic nor a license for inaction. It is simply the physics of delay. That is why comparisons with ancient catastrophes must be made carefully. Not every warming event should be called a new dinosaur-era hothouse, just as we should not console ourselves with the fact that Earth has survived stronger disturbances. For geology, the planet will survive almost anything. For agriculture, coastlines, forests, and human cities, the real question is different. Can our systems adapt as quickly as conditions change? If we map the 5 great extinction events, we will not find a single arrow pointing simply from simple to complex. We will find feedback loops. Ice reflects light and amplifies cooling. Volcanic carbon warms a frozen planet gradually. Oxygen rewrites the rules of metabolism. It eliminates ancient forms of life and opens the door to new ones. A predator forces its prey to build shells, and the shells change the chemistry of the ocean. An impact breaks the long chains of life and clears space for a different architecture of life. There is still an important distinction between fact and narrative. It is convenient to arrange history into a smooth sequence: impact, then oxygen, then ice, then complex life, then an asteroid. In reality, these eras overlap, and their boundaries depend on what exactly we choose to call a world. A single sequence helps us navigate the story, but it is not the only official chronology. Science measures layers and connections, and words like first and fifth are only tools to keep scale in view. This rule matters especially for numbers. 4.5 billion years is a rounded age of the Earth. 2.4 billion years is a marker for the Great Oxidation Event. 710 and 640 million years are dates of major glaciations, not two frozen snapshots. 541 million years marks the beginning of the Cambrian period in the modern geologic timescale. 66 million years is the age of the boundary linked to Chicxulub. Every date has a range and a method behind it, which is why we say approximately, when it truly is approximate. The main thread of this story is a change of scale. A cosmic impact becomes climate. Microbial chemistry becomes atmosphere. Ice becomes a filter for sunlight. An eye becomes a weapon, and a weapon changes the body. A rock becomes a dark winter, and a dark winter changes the evolutionary map. A cause matters only when we can trace it through the system and see it become an effect. The planet can be imagined as a set of linked clocks. Some measure rotation, others carbon, others reproduction and hunger. A catastrophe does not have to break every clock. It is enough for one mechanism to run faster than the others while the rest fail to keep up. After an impact, gravity keeps working. After the oxygen crisis, photosynthesis continues. After an ice age, volcanism remains. Life survives precisely because the system never disappears entirely, but the old synchrony never returns. Let us return to the morning window. The moon reminds us of the impact that ended the first surface. Iron-rich rock reminds us of bacteria whose waste became air. The glacial layer preserves the memory of a planet that nearly covered itself in ice. The Cambrian exoskeleton shows how vision and predation restructured life. The iridium layer under our feet marks the night after which large land animals disappeared. Even that final marker does not mean everything became empty. In the seas, microscopic food webs kept functioning. In fresh water, species survived. Some organisms could feed on debris, and on land, small animals waited out the darkest period in burrows and shelters. The transformation of the world is assembled from millions of private strategies for surviving one shared crisis. When we look at this series today, it helps to remove the illusion of inevitability. None of the 5 breaks was a pre-planned road leading to humans. The impact did not aim to create the age of mammals. Bacteria did not plan the oxygen atmosphere. And the survivors of Chicxulub did not know that tens of millions of years later, their descendants would occupy empty niches. Our present is not the finale of history, but just another configuration of conditions. The only question is how wisely we use the rare opportunity to observe it with our own instruments. The reliability of this picture rests not on a single striking proof. The user has provided a Russian source text and asked me to translate it into English. They've given detailed requirements: preserve every fact and detail, maintain paragraph order, keep the narration length suitable for a video script, and return only the translated text without any extra formatting. Looking at the content, this is a scientific commentary about Earth's history, mass extinction events, and humanity's relationship with planetary change. The tone is contemplative and educational, with a practical twist at the end where the narrator addresses the audience directly. It's likely narration for an educational video. The text explores how we reconstruct past extinction events through multiple lines of evidence, uses careful language with qualifiers and approximate dates, and draws parallels between ancient catastrophes and current environmental changes. The key point is that Earth itself is resilient, but the familiar world human civilization depends on may not be. The conclusion is somewhat philosophical, emphasizing agency and choice, and it ends with the expected social media engagement prompt. I need to maintain the thoughtful, slightly poetic tone while staying scientifically precise. The structure moves through scientific methodology, the nature of planetary change, practical implications, the resilience argument, and the call to action. I'll preserve the paragraph breaks, keeping any blank line separators as they appear in the original. The language is somewhat elevated and philosophical, not academic jargon, but thoughtful commentary. The challenge is keeping the English natural while preserving the contemplative narrative quality. Terms like follow-up or feedback for obratная связь need precise translation. In this scientific context, feedback loop or just feedback fits better than response. The translation should flow naturally for a video audience, maintaining that storytelling rhythm while being accurate about all the scientific claims. Time to translate. Each era requires at least 2 independent types of traces: chemical and biological, mineralogical and climatic, a crater and an extinction layer. The more lines converge, the less the reconstruction depends on a fortunate metaphor. That is why the imagery is accompanied by caveats and dates with the prefix approximately whenever measurement demands it. We call all of this the 5 catastrophes because humans need to count. But the planet has no closing credits. Every end was a transition for those who crossed the threshold, and a beginning for those who came after. The world does not choose just winners. It simply changes the conditions, and life sorts through the available solutions. There is also a practical purpose to such cautious language. If we name only a beautiful object as the cause, an asteroid, a volcano, or a glacier, we lose the chain of decisions. But if we see a threshold and a feedback loop, it becomes clearer where we can intervene. We cannot undo an ancient impact, but we can avoid accelerating the collapse of the food web afterward. We cannot command the ice to reflect less light, but we can account for how the change in dark water accelerates melting. We cannot bring back an oxygen-free atmosphere, but we can understand the cost of a chemical transition. Earth's history does not offer a ready-made instruction manual, but it teaches us to look not for a villain, but for a mechanism. The main takeaway sounds both unsettling and reassuring at once. Earth is not a fragile glass sphere that can be shattered by a single careless movement. It has survived impacts, global ice, and the poisoning of its atmosphere. But the planet's resilience does not mean the resilience of the familiar world. The planet will keep spinning even if the familiar coastlines, harvests, forests, or species our own kind have grown used to disappear. The question, therefore, is not whether Earth will survive humanity. Most likely, as far as storms go, yes. The question is which world will remain viable for humanity after the next transition. 5 times, the previous combination has not returned. Now, for the first time in the known history of our species, we have the digital watching on the human side. The air above us are not an eternal backdrop, but the result of ancient transformations. And what we add to it today will become part of the next layer. If you are interested in analyzing the planet by its planet, press like, write in the comments which part of the 5 turns you think is the most underrated and why. Subscribe so you do not miss the next episode. See you in the next route across Earth.